set up here. A couple of months ago, I gave a talk entitled Benjamin Franklin's Contributions to Fireplace Design. I think we could all learn a good deal more about the scientific method from Benjamin Franklin than you could by listening to me. Also about entertaining writing and persuasive argument. However, since I've been asked to talk about myself, I'll attempt to do that. Now, Jerry gave you a little bit of my background. One other point that probably should be mentioned was that I was an enthusiast. I started building model airplanes when I was 9 years old, and I always knew that I wanted to be an aeronautical engineer. I think you'll realize from hearing the talks yesterday that most of the people in charge of research here at Langley during the days of the NACA were enthusiasts. There was really nothing they'd rather do than aeronautical research. The first slide shows me sitting on top of a wind tunnel that was built in conjunction with the Jordan Traveler Junior Aviation League. This is when I was 21 and before I came to Langley. This was a rather unusual wind tunnel. It was intended for testing indoor models, had a test section 5 feet in diameter and an airspeed range of 3 to 5 feet per second. Now, I'm going to discuss the research by covering 4 different problems that we worked on, and these problems are not necessarily the ones that yielded the most important research results, but I think they serve to illustrate some of the different approaches that are used in solving these problems. Now, the problems are listed on this slide. We have the case of the unexpected instability, which is concerned with all movable horizontal tails, the case of the unexplained maneuver, roll coupling, the case of the unknown concept, gust alleviation, and the case of the unsuspected phase lag, pilot-induced oscillations. Those of you who watch Judge Wapner on TV will probably figure out where I got the inspiration for my titles. Now, the first work, the case of the unexpected instability, was work that was conducted starting about 1942. Previously, Bob Jones had done some work on a concept that he called the all-movable tail surface, and his idea was, instead of using a surface with a fixed section and a movable flap, he would hinge the entire surface, and then a geared tab was attached to the trailing edge of the surface. By adjusting the position of the hinge line and by setting the correct gearing between the tab and the main surface, it was possible to adjust the hinge moments as desired. Also, if the hinge line were behind the aerodynamic center of the tail, then the tail would tend to float against the relative wind and thereby give more stability to the airplane than a fixed surface. Also, since the tab moved in the same direction as the rest of the surface in that condition, you had a condition where the surface was at an angle of attack and with a deflected flap, so it was a very good configuration for getting high maximum lift. And thereby it was possible, with a surface of this type, to stabilize the airplane with a smaller area than with a conventional tail surface. Well, we tested a surface as a vertical tail on a Fairchild F-22 airplane. This was a small parasol wing airplane that was used in quite a bit of the early NACA research. And the results were quite successful. It demonstrated that a tail of smaller area was able to do the same job as the original tail on the airplane. However, I'd like to talk mainly today about the application to a horizontal tail surface. The next slide shows this surface installed on a Curtiss XP-42 airplane. You can see the experimental tail surface there. The next slide, please. Now this shows a close-up. You can see, in addition to the tail here, the tab on the trailing edge. This slide shows a plan view of the airplane showing the comparison of the tail with the original tail. Now, this tail was suggested by Bob Gilruth and had a somewhat different concept from the idea suggested by Jones. At that time, fighter airplanes were running into problems in high-speed dives because they would reach speed where compressibility effects were encountered on the wing, and shock waves would form, which would cause the flow to separate on the wing. Usually this resulted in a large loss of downwash at the tail, and as a result, a large nose-down pitching moment on the airplane. And because these airplanes in dives were at very high dynamic pressure, sometimes the pilot was unable to pull hard enough on the control stick to recover from the dive. So the idea of this tail was to reduce the aerodynamic hinge moments on the surface practically to zero, so that the problem of applying enough control effort would not be encountered. Now, the principle of operation of the tail is shown on this slide. The tail was pivoted about a point close to the aerodynamic center so that the forces required to deflect it would be small in any case. Then the tail was controlled through a device we call a spring tab, which is this linkage. And this slide shows, this second figure shows how this would work. If you pull on the control stick, that first deflects the tab. Then, as the tail moves in response to the aerodynamic forces, the tab then again becomes lined up with the surface. And also a spring is inserted between the control linkage and the main part of the tail. The spring is weak enough, however, so that the aerodynamic forces have the main effect in moving the tail. The main purpose of the spring is so the pilot can move the tail around by moving his stick when the airplane is sitting on the ground. Now, since the spring tab arrangement would reduce the control forces practically to zero, a field device in the form of a bob weight on the control stick was added. This would give a constant force per G when the pilot made pull-ups and turns, and we had found from previous handling qualities research that this was a desirable type of control field. Well, our chief test pilot, Mel Goff, took this airplane out and made some high-speed taxi runs and shot hops into the air. And he came back and very vehemently said that this airplane was completely uncontrollable, and under no conditions would he fly it until we made some improvements in it. So this was somewhat of a puzzle. We thought that the tail would work reasonably well. We thought the aerodynamic center would be at the quarter chord point, and the tail was pivoted at the 24% chord point so as to give it a small amount of stability. Well, after thinking about this without coming up with any solutions, I decided to build a model. This wasn't a model of the XP-42 by any means, just a glider model with a rectangular fuselage. The wing was taken from an old rubber-powered model that I had available. And however, the tail and the tab linkages and so forth were quite well reproduced. Since I'd had a lot of experience building models, I could build a model like this in about a week. And when this model was glided, it immediately went into a very very violent pitching oscillation with the tail banging back and forth against the stops. It was immediately apparent on looking at that model fly that this tail was overbalanced. By that we mean aerodynamically overbalanced, so that when the tail started to deflect, it would immediately go to full deflection. Well, that caused us to look up some data on the factors that might affect the aerodynamic center of a tail surface. And this slide shows three effects, at least, that might cause the aerodynamic center to be further forward than we had planned. First, although we usually consider that the aerodynamic center on an airfoil is at the quarter chord point, it's true that on a finite aspect ratio surface, the aerodynamic center is further forward. Perhaps even some aeronautical engineers today don't realize this. The other point is that this surface had a finite trailing edge angle. Many airfoils are designed with a cusp-type trailing edge, but when the structural engineer sees this, he fills in the surface back here with lines tangent to the upper and lower surfaces in order to get more thickness for structural strength back at the trailing edge. And this had been done on this airfoil. Now, Bob Jones had previously put out a report which showed that you could reduce the hinge moments on a control surface by using a beveled trailing edge. And it was generally known at that time that the trailing edge angle did affect the hinge moments on the control surface. Well, that also occurred on the all-movable tail, and since we had this finite trailing edge angle, that further tended to move the aerodynamic center forward. Finally, as you can see, when the tail is deflected, the tab tends to float with the relative wind, and the aerodynamic forces generated tend to further deflect the surface. So the combination of these three effects evidently combined to make our tail quite unstable. Well, this was corrected by gluing strips along the trailing edge. These were strips strips of wood about 1/4 of an inch high on the upper and lower surfaces, right at the trailing edge. This was a fairly common procedure in those days for increasing the hinge moments of a control surface. And when this was done, the surface was found to be sufficiently stable so the pilot was able to continue the flight research. Now, the handling qualities were still not completely satisfactory, and so it might be of interest to discuss a little bit what we learned from these studies of all movable tails. First, in connection with the vertical tail, as I mentioned, the tail itself worked satisfactorily. However, at that time, a big issue was what we call snaking oscillations. A lot of airplanes had this tendency to do a small amplitude, continuous oscillation in flight, and nobody could quite come up with the explanation as to why this happened. Some people thought it was due to alternate flow separation from the sides of the fuselage or from the wing fillet area. Other people thought that it was just a response of the Dutch roll oscillation to small amplitude atmospheric turbulence. But I think the correct explanation was first given by George Scherer of the Boeing Company. They had encountered this oscillation on the Boeing 314 flying boat, and his explanation was that when the airplane side slipped a small amount, the rudder had a tendency to float against the relative wind. It caused the airplane to swing back the other way, but the friction held the rudder until it had deflected, until the side slip had changed to the other direction and built up enough so that it overcame the rudder friction, and the rudder would flop over the other way and the airplane would swing back, giving a continuous limit cycle oscillation. The oscillation was quite small amplitude, usually about 1 degree, and only about 1/10 of a degree rudder motion would be required to produce an oscillation of this amplitude. Now, our instruments in those days were not sensitive enough to detect that smaller rudder movement, and certainly nobody in wind tunnel tests had studied the hinge moments on a surface for deflections or side slip angles as low as 1/10 of a degree. So this this sort of thing tended to remain obscure until this explanation was given. However, with our all-movable tail on the F-22, we were able to vary the hinge moment characteristics quite readily into the range that would produce snaking, and we could vary the control system friction, so we could demonstrate snaking oscillations of any desired amplitude, and this served to tie down this explanation as the probable cause of most of the troubles that were encountered by the airplanes having this problem. Well, now coming to the horizontal all-movable tail, this airplane was never used or never intended to do high-speed dives, so we could not directly demonstrate the ability of this surface to cure this problem. However, as I mentioned, we did have some problems with the handling qualities. Now, it wasn't too long after that hydraulic control systems were introduced on airplanes, and with these systems, again, the hinge moments on the surface were reduced to zero, and the designer had to supply some kind of a feel device to give the pilot adequate control feel. Well, we found that the reason the bob weight was unsatisfactory was that it gave the pilot no warning of how much acceleration he was going to get when he pulled on the control stick. In other words, he'd pull back on the stick to make a pull-up, but the control force didn't start to build up until the acceleration increased. So he didn't know how much G he was going to get. We found it was necessary to put some force in phase with the control deflection in order to get adequate control feel. And this system was later modified to provide that feature. Well, the reason this is important was that when airplanes did come out with hydraulic control systems, then we were in a position to advise industry and advise the designers as to what characteristics were required for satisfactory control feel. Well, I'd like to go on now to the next topic, which is the case of the unexplained maneuver, roll coupling. You can take off that slide now, please. Of all the work I've done at Langley, this is probably the job that has received most recognition. For example, it's the only one that was noted in the 25 years ago today column in Astronautics and Aeronautics. This work was published in 1948, and this little article came out in 1973. It says, NACA research scientist William H. Phillips of the Langley Memorial Aeronautical Laboratory Flight Research Division publishes NACA technical note TN 1627, which contains a theoretical prediction of the problem of inertial coupling. The phenomenon later plagues aircraft having long fuselages and short wings, where the mass of the load is spread along the fuselage with little span-wise distribution of load. In particular, it forces a slowdown in the operational introduction of the North American F-100A Super Sabre, and first manifests itself in flights of the Douglas X-3 research plane, and so forth. Also, when I made trips to England and Germany some years later, people would say to me, "Oh, you're the roll coupling Phillips." Well, several people have asked me, how did I happen to hit on this idea? And up to now, this has been a deep, dark secret. But today I'll reveal to you how this came about. Actually, the secret was partly let out of the bag by Chris Kraft when he gave a colloquium lecture here. Now, at that time, NACA was making studies of the aerodynamic drag of bodies at transonic speeds by dropping heavily weighted models from a B-29 airplane at 35,000 feet. These models would reach speeds of about Mach numbers of 1.1 to 1.2, and by telemetering the drag data, it was possible to measure the drag through the transonic speed range. This was desirable, or this was done in those days, because wind tunnels capable of going through transonic speeds had not yet been developed. Now also the X-1 airplane, then called the XS-1, was being developed, and we thought we could extend this bomb drop procedure to study the longitudinal stability of an airplane at transonic speeds. So a model was made of the XS-1 airplane. This is a photograph of the model. You can see the telemetering antenna at the front. The model was machined out of solid steel. It had a opening in the fuselage, of course, for instrumentation. Also, a simple longitudinal autopilot was incorporated because we didn't know what pitching moments would be encountered at transonic speeds. This autopilot was simply an accelerometer sensing normal acceleration with a couple of contacts on it. And when the acceleration exceeded a range of 4/10 to 8/10 g, these contacts would operate and actuate a slow-moving trim motor, which would run the elevator in the direction to bring the acceleration back into the desired range. Now the next slide shows a 3-view drawing of the model. As you can see, it had a... Want to move it up, please? Could you move it up, please? Yeah. It had a span of 84 inches, or 7 feet, and the weight was 1,350 pounds. Pretty heavy model for that size. Now, when I fly a model airplane, I frequently sight along the trailing edge of the wing to make sure it's not warped before I launch it. Nobody would have suspected that this wing would be warped, since it was machined from solid steel to an accuracy of 0.02 of an inch. However, as a matter of habit, I looked along the trailing edge of the wing, and I could see it was quite apparent to me that this wing was warped, and the one side was up about 1/4 of an inch compared to the other. So some more accurate measurements were made and showed that sure enough it was warped. So some small wedges were placed on the trailing edge of the wing, similar to ailerons, to attempt to offset the twist, or the built-in twist of the wing. We did not want the model to roll too fast during the dive because we were studying longitudinal characteristics. Well, the model was dropped, and the time history of the results are shown on the next slide. You can see that the acceleration starts off around the Mach number starts off at about 5/10 and builds up to very nearly 1, and then decreases a little bit towards the end of the dive. This shows the transverse acceleration, the longitudinal acceleration, which shows the buildup of drag during at transonic speeds, the normal acceleration, and the elevator angle. Now the acceleration started off less than 4/10 of a g, and as a result, the elevator, as you can see, ran up to its full up deflection, which was 10 degrees. When the acceleration exceeded 8/10 of a g, the elevator started moving down again, as was intended, and it maintained the acceleration in the desired range fairly well. Towards the end of the drop, however, you can see the elevator was full down. Its maximum downward deflection was 4 degrees, but this was not enough to keep the g from building up, and it built up to about 2g. Now, a rather unusual thing happened also. We did not measure the rolling velocity, but the people tracking the model with a phototheodolite could see it rolling by the flashing of light on the wings. However, when we got about to this point, near the maximum Mach number, the model stopped rolling, and due to the 2g acceleration, it performed a gradual pullout. So it flew away far from the desired impact point at Plum Tree Island, and flew way over to the swamps of Poquoson and crashed down there. Now, it's not considered very good to have a 1,300-pound model at Mach 1 crashing down in a populated area. However, apparently no one knew about this, no one was hurt, so far as I know, no attempt was ever made to recover the model, and it's probably still sitting 20 feet deep in the mud somewhere around the swamps of Pocosin. And very little was ever said about this. Well, there was one rather interesting point, though. When we came to examine the data, you see this rather violent oscillation occurring. This does not occur in the range where we expect serious compressibility effects. It starts around Mach number 7/10. And it's a sufficiently violent oscillation so that it's going from plus or minus 1 G, which is about at that condition is to the positive and negative stall. Well, this was quite surprising. Of course, we knew that airplanes did violent maneuvers in snap rolls, but this was due to the fact that when you pulled up, the wing stalled and caused unusual aerodynamic moments, and so the snap roll was not considered anything unusual. In this case, however, the airplane is oscillating about a condition of zero lift. Well, I felt, because of the fact that the model was rolling and also the very heavy weight of the model, there were probably some inertial effects involved. So I started to think about how to investigate this problem. Now, I must admit that it never occurred to me that the conventional airplane stability equations could be used to study this problem. Probably the reason for this was that when I studied stability at MIT, the professor first introduced the longitudinal equations and then the lateral equations, and these were studied as separate problems, whereas in this case we had a combination of longitudinal and lateral motion. At MIT, however, I had a course called Introduction to Aeronautical Dynamics by Professor Rauscher, in which he went back to first principles and introduced us to a set of equations called Euler's dynamical equations for the rotation of a rigid body. And these equations are shown on this slide. Now, since these equations applied to combine the longitudinal and lateral motions, I thought this would be a good way to start investigating the problem. Now, the first equation states that the rolling moment is equal to the rolling inertia times the rolling acceleration minus a term involving a product of two angular velocities, pitching and yawing velocities, times the difference of two of the moments of inertia. And the other equations have similar form. Now, I felt that in this maneuver, the airplane was rolling at approximately a constant rate, so the rolling acceleration would be zero. Also, Q and R would be small, so the product would be negligible, and so this entire first equation could be neglected. The second two equations, we see this product RP and PQ involving the rolling velocity. However, if the rolling velocity is constant, then the equations become linear, involving Q and R. Now, this was fine because I knew how to solve linear equations. The other point you can see is that the first two terms are simply the equations of a body doing a single degree of freedom. The pitching moment equation represents a pitching oscillation in pitch, and this one represents a yawing oscillation. The effect of these terms is to couple those two oscillations. So the way I approached this problem was to consider a vehicle having an oscillation in pitch and an oscillation in yaw, which were coupled by those coupling terms, hence the term inertial coupling that was applied to this work. Well, this seems like a straightforward approach. However, I did run into some conceptual difficulties. It appeared that when the pitching and yawing oscillations were studied, it was probably more convenient to use fixed axes, whereas the Euler's equations apply to angular velocities about body axes. And so if I used body axes, I had to resolve the components of the rolling velocity about the body axes, about the fixed axes, in order to, I'm getting this a little mixed up. I guess I should say if I analyzed it with respect to fixed axes, I first had to resolve the rolling velocity about the x-body axis about these fixed axes, and thereby get some additional terms in the Euler equations. I was quite uncertain whether this should be done or not. It seemed to me that with this small amplitude oscillation, it really didn't make much difference whether it was considered about fixed axes or body axes. So the thing I did was to work it out both ways, and then it appeared when I did not resolve the rolling velocity that I got some results in certain limiting cases which were unreasonable. So that's the way I determined which was the correct approach. Well, with this solution, it was possible to plot some stability boundaries, such as those shown on this chart. This shows the longitudinal stability in terms of a parameter omega sub theta squared, and directional stability omega sub psi squared. Omega sub theta is defined as the ratio of the pitch natural frequency to the rolling velocity, or the rolling frequency. Similarly, omega sub psi is the ratio of the yaw frequency to the roll frequency. Normally, if an airplane would have some pitch and roll frequency, and so we would be located somewhere in this chart. And as the rolling velocity increases, since the rolling velocity is in the denominator, you would follow a set of conditions approaching the origin. Now, if the pitch and roll frequencies are approximately equal, the airplane, or the conditions, would go on this path which would remain in the stable region all the way up to infinite rolling velocity. However, if the pitch and roll frequencies were different, then it's possible that the conditions would cross over the boundary into this region of divergence. It appeared that that was what happened on the X1 model. That is, we knew in that case that the directional stability was very much larger than the longitudinal stability, so the conditions would be somewhere in this region, and as the rolling velocity increased, it would pass over into this divergent region. Evidently, when that happened, the airplane simply diverged until it reached the stall, and then the stability increased to the point that it was batted back in the other direction, resulting in an oscillation of several cycles, as you saw. Well, when I wrote a report on this, I pointed out that although this problem had not been encountered on full-scale airplanes up to that point, that it would very likely be encountered on fighter airplanes, which were then on the drawing boards, because these airplanes had most of their weight in the fuselages and short wingspan, high rolling velocities, all conditions which would tend to lead to this problem. And as you heard, this was actually encountered, and as a result, this report got quite a bit of attention. Well, I'd next like to go to what I'd call the case of the unknown concept, which is gust alleviation. Let's see, I really didn't mean to put that slide up yet, but that's okay. This work was started about, about 1949, went on into the 50s. At that time, automatic controls were becoming sufficiently reliable to be used fairly extensively on airplanes, and it appeared that the real future of stability and control research would be to study the applications of automatic controls. Autopilots had been pretty well perfected during World War II, and at that time, pitch dampers and yaw dampers were just coming into use. However, these were conceptually so simple, it hardly seemed worthwhile to do any research on them. That left about 3 fields where we thought there would be worthwhile research. One was the study of guided missiles. The other was what we call command control systems, where the pilot's input is applied through the automatic control system. This is what we sometimes call today active control systems. And finally, the subject of gust alleviation. Now, the guided missile work had been pretty much ruled out because Dr. Dryden, when he was administrator, said that NACA shouldn't work on guided missiles unless they were requested by the military services. That left the command control systems and gust alleviation, and we did research in both those areas. I'd like to talk about the gust alleviation because I was more directly involved with that. Now, at that point, a number of attempts had been made to build gust-alleviated airplanes, but these had all been notably unsuccessful. And I concluded the reason for this was that these were all attempts to build airplanes by inventors who had not bothered to do any theoretical analysis of their systems before they were tried. And as a result, I thought the best approach to this problem would be to first make a theoretical analysis. Now, this was something I could do quite easily on the basis of my background, because I was involved primarily with the longitudinal equations. These equations were first developed by Bryan in a report as early as 1904. In fact, Bryan set up the complete 6-degree of freedom equations for an airplane, then divided it into the longitudinal and lateral modes. Then he introduced the concept of stability derivatives and carried out solutions. In fact, there was very little improvement from that point to the classical stability theory to this day. In 1911, he put out a book, Stability in Aviation. Now, this method was extended to include the effect of gusts by a report by E.B. Wilson, which was actually Part 2 of NACA Report Number 1, published in 1915, called Theory of an Airplane Encountering Gusts. After that point, there was very little improvement in the theory. One improvement that did appear to be worthwhile was introduced by Cowley and Glauert in 1923. This was called the effect of lag of downwash. This means that when the airplane is changing angle of attack, the wing sheds some downwash, but the downwash does not reach the tail until a short time later. That is the time required to the airplane to go a distance equal to the tail length. And it was found that this could be incorporated by an additional stability derivative, that is a moment proportional to the rate of change of angle of attack. Since I wanted my theory to be as accurate as possible, I decided to incorporate this effect. And also there were other lag effects when you considered gusts, known as gust penetration effects. That is, the gust first hits the nose, then the wing, and then the tail, so there's a lag between hitting different parts of the airplane. Also, I plan to use flaps on the wing to offset the effect of gusts, and when the flap is deflected, then the flap downwash reaches the tail after a certain time lag. So it appeared that I could incorporate these effects using the same simple theory that was introduced by Cowley and Glauert. We might call this a first-order theory, since it did not increase the order of the equations a great deal, simply introduced one additional term. Well, that theory was carried out, and one of the methods of approach was to use what we call the frequency response method. That is, it was possible to assume sinusoidal gusts of various frequencies and calculate the response of the airplane. The resulting expressions are called transfer functions. Now, I got the transfer function for the normal acceleration and for the pitching velocity, and by setting the numerator of that expression equal to 0, I could solve for the flap characteristics required to give normal acceleration of 0 during flight through gusts. When I did this, I found that I could solve for the flap characteristics, but the pitching response was increased considerably. So then I thought, well, I can set the numerators of both the normal acceleration and pitching velocity transfer functions to 0 and solve for two conditions, which would then give complete gust alleviation. Well, I did this, and it was possible to solve for certain characteristics of the flap, namely the flap effectiveness and the variation of downwash with flap deflection. Now, this was in terms of a mathematical formula, but after thinking about this for a while, I could see that this actually represented a very simple physical concept. What's going on is, assume we have an airplane approaching a step gust. When the gust hits the wing, it's necessary to move the flap up to produce a lift just opposite to the lift generated by the gust on the wing. However, when you do this, this causes a pitching moment on the airplane. Now, this pitching moment can be offset by simultaneously deflecting the elevator. So if that is done, then the pitching moment is also 0. Then when the gust reaches the tail, that produces a lift on the tail. Flap and elevator are still deflected. In order to offset that lift on the tail, one possibility is that the downwash from the flap would just offset that lift on the tail, since it would reach there the same instant as the gust. Now, this is somewhat unfortunate in that you can see that when the flaps are deflected up, it usually produces an upwash, whereas what we need is a downwash. However, we actually considered various possibilities and decided to build an airplane in which this principle would be utilized. Another way to do it would be to then subsequently deflect the tail an additional amount, the elevator an additional amount, to offset this lift on the tail due to the gust. I'll explain in a minute why that was not done. Now, the next slide shows the airplane that we modified to include a gust alleviation system. This is a Beech B-18 airplane, also known by the Everest designation C-45, and you still see a number of these flying around as executive airplanes. You can see we installed a vane on the nose to sense the gusts. Now, the vane operated the wing flaps through a hydraulic servo mechanism, and the flaps were modified to be full span flaps, which would deflect both up and down. However, a small section of the flap at the inboard end was arranged so that it could be deflected in the opposite direction from the remainder of the flaps. The purpose of this was to throw off a downwash which would hit the tail in the opposite direction from the downwash from the rest of the flap system. In addition, as you can see, the elevator was divided into 3 sections. The center section remained connected to the pilot's control stick, and the outboard sections were geared to the flap system. Now, in those days, we had to use vacuum tube servo mechanisms, and these servo mechanisms were notorious for changing gain. In my analysis, however, I found that the gain between the flaps and the elevator was very critical. In other words, since the flap deflects in phase with angle of attack, any pitching moment due to the flap system directly affects CM alpha, the longitudinal stability of the airplane. And just a small variation in this gearing between the flaps and the elevator might easily make the airplane go unstable. So we figured it was safer to use a rigid linkage between the flap system and the elevator. And this was later shown to be a wise choice, because when we made the flights, the gain between the vane and the flaps was usually changing all over the place, and this didn't affect safety of flight. It just affected the amount of gust alleviation we could get, but we were safe as far as having the correct CM alpha. Well, this airplane, so you can remove that slide, please. Now let's take that off now, please, for a while. The results with this airplane were quite satisfactory. We got accelerations in turbulence reduced to about 40% of those of the basic airplane. The main reason we did not do better was because of faults in the servo mechanism itself. That is, the servo mechanism, which was a variable displacement pump type, was very severely rate limited, so that in larger amplitude turbulence it couldn't move the flaps fast enough to keep up with the turbulence. It's been one of the big disappointments of my career that the aviation industry has so completely neglected the possibilities of gust alleviation. We don't see any transport airplanes today flying around with alleviation systems, at least not which would alleviate the rigid body motions of the airplane. And the few attempts that have been made to study gust alleviation systems since then have been what I would consider steps backward, because they usually did not consider many of the effects that I found to be very important. For example, it's often been the case that such things as flap downwash have been completely neglected, and so it's a subject which still, I think, offers great possibilities. If this were done today, I think it could be done with very little performance penalty and with very little weight addition to the airplane, because of the perfection of the servo mechanisms. And the other point is that probably today we would not gear the flap system to the elevator, but would use a separate servo mechanism on the elevator, which would enable a greater flap effectiveness to be obtained and make a more satisfactory system. There is a project at NASA at present to install a gust alleviation system in a small twin-engine Cessna. I suspect it'd be much a repeat of the program we did 30 years ago, but hopefully it will lead to greater interest in the part of the industry. Well, I'd like to proceed now to the last topic, the case of the unsuspected phase lag, or pilot-induced oscillation. This was a problem that we first started to study about 1952. That was when hydraulic systems were being introduced into control systems, and when that happened, quite a few airplanes encountered these pilot-induced oscillations. In this case, a pilot may be maneuvering or flying the airplane in some task. Suddenly, he starts an oscillation, and as he tries to damp it out, instead he causes it to build up, and sometimes to a rather frightening amplitude. Well, the main reason I introduced this subject is this is the only one I can think about where The idea of how to solve it sort of came to me in a flash, and sometimes this is considered of interest to people studying thought processes. I'm sure it didn't occur when I was at work. It was probably when I was at home. And I remember the next day I came in and was enthusiastic about studying this technique, and the other engineers were very unconvinced that it would ever lead to any useful results. And I have the next slide. These are the things we knew about pilot-induced oscillations. They were encountered with hydraulic control systems. They were believed related to the force characteristics rather than displacement characteristics of the system. And valve friction was a suspected cause. In these hydraulic systems, when the pilot moved the control stick, it deflected a small hydraulic valve, which then allowed fluid to flow to the main hydraulic cylinder. The next slide shows how this valve friction might influence the control characteristics. Suppose the pilot starts to move the control stick. He pulls on the stick, but nothing happens until he breaks through the valve friction. Then the valve is deflected, and the elevator starts to move at a constant rate. Now the pilot may decide then that he doesn't want the elevator to move further, so he starts pushing in the other direction, but then the elevator does not start to reverse until he breaks through the valve friction in the other direction. Then the control moves in the other direction. And as you can see from this chart, the control force is exactly 180 degrees out of phase with the resulting response. We knew from previous work, as I mentioned, that we would really like the control force to be in phase with the elevator deflection. So this was thought to be a possible source of these oscillations. However, the problem was to convince anybody of it. The thing was that if you sat in the cockpit in an airplane with a hydraulic system and moved the control stick, it moved just as smooth as could be. You couldn't see anything wrong, you couldn't feel anything wrong. I thought, this is my idea that came to me as to how we might demonstrate this problem. This is called the frequency response method. We would first measure the stick forces and elevator deflections with sinusoidal inputs of various frequencies and amplitudes. I should have mentioned, we had an airplane that we'd obtained from the Navy with a hydraulic system installed for experimental work. So we could run these measurements, then calculate the pitching response of the airplane to sinusoidal elevator inputs. Then third, we would assume a relation between the pilot force output and the airplane pitching velocity. In other words, we'd assume a pilot transfer function. And finally, put all these factors together as a closed-loop system and use the Nyquist stability criterion. I mentioned the reason pitching response was used, that is pitching velocity, was that this is the thing with the least lag. In other words, when the pilot deflects the stick, the pitching response occurs first, then the angle of attack, and then the pitch angle. So we figured if we showed an oscillation when the pilot sensed pitching velocity, this would be the most convincing type of demonstration. And also we knew the pilot could sense pitching velocity because the pilot has an inner ear mechanism which enables him to sense pitching velocity. Well, when this was done, sure enough, showed we had instability. Now, this might seem like a very conventional thing to do nowadays, so I might point out what are the original aspects of this analysis back in those days. First, control forces rather than deflections were considered as the primary pilot output. Almost all the work on servo mechanisms to that day had been done assuming a control deflection was the output. Second, the analysis of the human as a servo mechanism or black box. Some work had been done, of course, by that time on human pilot response. A man named Tustin during World War I used pilot transfer functions to design anti-aircraft gun directors. But very little had been done using these techniques on airplanes, and in particular the use of the pilot's force output had not been considered. Now, in addition to doing this analytically, we set up a demonstration so the pilots could feel it and convince themselves that they had a tendency to pilot-induced oscillations. This is what we call an early simulator. In those days, we didn't have analog computers, didn't have any simulators. However, we hooked up a slide projector on a frictionless pivot to the elevator by means of a spring, so that when the elevator was moved, this slide projector would oscillate with a motion very similar to the pitching response of the airplane, pitching velocity response. Then the light from the projector was projected to a screen next to the pilot cockpit, so we had a fairly sensitive movement of the light spot to the pilot's control input. Well, as I mentioned, when the pilot just sits in the cockpit and moves the stick, he can't feel anything wrong at all. But when he tries to maneuver this light spot, he soon recognizes, or immediately recognizes, the tendency to pilot-induced oscillations. Today, of course, we have many simulators which can be used for studies of this type. Also, when every new airplane is built, the control system is laid out on the floor in a mock-up called an iron bird, and this might be called the forerunner of the iron bird. Today, they set up the control surfaces, usually with simulated inertia and control loading devices, and the motion of these simulated surfaces is fed into a computer, and the computer calculates the resulting motion of the cockpit instruments, so that many problems of this type can be solved before the airplane actually is flown. Only one point I might mention, that is, one pitfall of using simulators or iron birds is that the display might not be sensitive enough to detect all the problems. We know that a human pilot, sensing by seat of the pants, can detect an oscillation of, say, about 2,000ths of a G. And if we give him a pilot display of a dial-type instrument, he may not detect accelerations anywhere near this small. So for these type of studies, it's very desirable to amplify the display as we did here, where we had about 1 G corresponding to a foot deflection of the pointer. Well, that concludes my various problems. I would like to just go through a few conclusions here. Some of these are maybe so obvious that they don't really need repeating. But my first conclusion is that new knowledge of flight control systems is likely to come only from experiments. None of these things I've talked about today could have been done if we hadn't been running experiments. Second point is the important results of experiments will probably be different from those expected. One application of this is that I think when we justify programs at headquarters nowadays, we frequently want to demonstrate some results of previous research. However, the main justification for flight programs shouldn't be this. It should be that we may learn something new. And it's sometimes hard to convince people making these presentations to include this aspect in it. Third, the ability of an engineer to solve problems depends largely on his educational background. This was brought out by John Hobolt yesterday, and it's certainly true in my case that it was definitely necessary to get up to date on the theoretical techniques and so forth before I could attempt to solve any of these problems. Finally, don't neglect the old NACA and NASA reports. A lot of good information in these reports that might still be applicable to today's problems. I might add, don't forget to consult your friendly DRA if you have trouble finding some of these old reports. So that concludes my presentation. Some work on a concept that he called the all-movable tail surface, and his idea was, instead of using a surface with a fixed section and a movable flap, he would hinge the entire surface, and then a geared tab was attached to the trailing edge of the surface. By adjusting the position of the hinge line and by setting the correct gearing between the tab and the main surface, it was possible to adjust the hinge moments as desired. Also, if the hinge line were behind the aerodynamic center of the tail, then the tail would tend to float against the relative wind and thereby give more stability to the airplane than a fixed surface. Also, since the tab moved in the same direction as the rest of the surface in that condition, you had a condition where the surface was at an angle of attack and with a deflected flap, so it was a very good configuration for getting high maximum lift. And thereby it was possible, with a surface of this type, to stabilize the airplane with a smaller area than with a conventional tail surface. Well, we tested a surface as a vertical tail on a Fairchild F-22 airplane. This was a small parasol wing airplane that was used in quite a bit of the early NACA research. And the results were quite successful. It demonstrated that a tail of smaller area was able to do the same job as the original tail on the airplane. However, I'd like to talk mainly today about the application to a horizontal tail surface. The next slide shows this surface. Then the tail was controlled through a device we call a spring tab, which is this linkage. And this slide shows, this second figure shows how this would work. If you pull on the control stick, that first deflects the tab. Then, as the tail moves in response to the aerodynamic forces, the tab then again becomes lined up with the surface. And also a spring is inserted between the control linkage and the main part of the tail. The spring is weak enough, however, so that the aerodynamic forces have the main effect in moving the tail. The main purpose of the spring is so the pilot can move the tail around by moving his stick when the airplane is sitting on the ground. Now, since the spring tab arrangement would reduce the control forces practically to zero, a field device in the form of a bob weight on the control stick was added. This would give a constant force per G when the pilot made pull-ups and turns, and we had found from previous handling qualities research that this was a desirable type of control field. Well, our chief test pilot, Mel Goff, took this airplane out and made some high-speed taxi runs and short hops into the air. And he came back and very vehemently said that this airplane was completely uncontrollable and under no conditions would he fly it until we made some improvements in it. So this was somewhat of a puzzle. We thought that the tail would work reasonably well. We thought the aerodynamic center would be set up here. A couple of months ago, I gave a talk entitled Benjamin Franklin's Contributions to Fireplace Design. I think we could all learn a good deal more about the scientific method from Benjamin Franklin than you could by listening to me. Also about entertaining writing and persuasive argument. However, since I've been asked to talk about myself, I'll attempt to do that. Now, Jerry gave you a little bit of my background. One other point that probably should be mentioned was that I was an enthusiast. I started building model airplanes when I was 9 years old, and I always knew that I wanted to be an aeronautical engineer. I think you'll realize from hearing the talks yesterday that most of the people in charge of research here at Langley during the days of the NACA were enthusiasts. There was really nothing they'd rather do than aeronautical research. The first slide shows me sitting on top of a wind tunnel that was built in conjunction with the Jordan Traveler Junior Aviation League. This is when I was 21 and before I came to Langley. This was a rather unusual wind tunnel. It was intended for testing indoor models, had a test section 5 feet in diameter and an airspeed range of 3 to 5 feet per second. Now, I'm going to discuss the research by covering 4 different problems that we worked on, and these problems are not necessarily the ones that yielded the most important research results, but I think they serve to illustrate some of the different approaches that are used in solving these problems. Now, the problems are listed on this slide. We have the case of the unexpected instability, which is concerned with all movable horizontal tails. The case of the unexplained maneuver, roll coupling. The case of the unknown concept, gust alleviation. And the case of the unsuspected phase lag, pilot-induced oscillations. Those of you who watch Judge Wapner on TV will probably figure out where I got the inspiration for my titles. Now, the first work, the case of the unexpected instability, was work that was conducted starting about 1942. Previously, Bob Jones had done this, installed on a Curtiss XP-42 airplane. You can see the experimental tail surface there. The next slide, please. Now, this shows a close-up. You can see, in addition to the tail here, the tab on the trailing edge. This slide shows a plan view of the airplane showing the comparison of the tail with the original tail. Now, this tail was suggested by Bob Gilruth and had a somewhat different concept from the idea suggested by Jones. At that time, fighter airplanes were running into problems in high-speed dives because they would reach speed where compressibility effects were encountered on the wing, and shock waves would form, which would cause the flow to separate on the wing. Usually this resulted in a large loss of downwash at the tail, and as a result, a large nose-down pitching moment on the airplane. And because these airplanes in dives were at very high dynamic pressure, sometimes the pilot was unable to pull hard enough on the control stick to recover from the dive. So the idea of this tail was to reduce the aerodynamic hinge moments on the surface practically to zero, so that the problem of applying enough control effort would not be encountered. Now, the principle of operation of the tail is shown on this slide. The tail was pivoted about a point close to the aerodynamic center so that the forces required to deflect it would be small in any case.